Okay, in this lesson, we're going to look at two methods for approximating roots of polynomials by hand. So our first method is the bisection method. So let's focus on this one. Okay, it's used to approximate roots of polynomials. And the way it works is we find 2 points, A and B, such that A is less than B, and the y values of each are different signs. In other words, is what this is saying. Okay, so one of our points is to the left of our x, the other one is to the right. Okay, and all we're going to do is we're going to keep bisecting those 2 points to approximate where our root is. So we cut the distance of between those points in half. We have one new point, one of our old points, and we continue to do that, containing our x-intercept until we get a good approximation of our root. Okay, so as far as rounding goes, we don't want to round our x values using this method, but our y values can be rounded to 3 decimal places. Okay, so let's look at an example. First example says the function f of x, which is x cubed minus 4x squared plus x plus 1, has a 0 between x equals 3 and x equals 4. So they tell us kind of where our bounds are. So we're looking at a root between 3 and 4. We want to use the bisection method to approximate the actual 0 of the function. Okay, now we've got a nice little skeleton that we're going to fill in for our iterations. We're going to do 4 iterations, so each time theoretically we'll get closer and closer to the root. Alright, so our first iteration, what we want to do first is we want to fill in, we want to find f of our 2 bounds. Our lower, which is 3, and our upper, which is 4. Okay, so we're just going to evaluate our function for each of these numbers to find their y coordinates. So if we plug in 3 into our function, 3 cubed is 27 minus 4 times 3 squared. So we've got 27 minus 4 times 9 is 36. And then we add 3 and 1 to that. Okay, so we do the math and we get -5 for our y value. Doing the same thing for 4, if we plug 4 into our function, save some time, then we get 5. Next thing we want to do is, since we're doing the bisection method, we want to find, in essence, the midpoint of these 2 points, the average of these two. 3 and 4, the average is 3.5. So now we want to evaluate our function for 3.5. Now, when you're asked to do this on a quiz or a test, you will be allowed to use a calculator for this part, so you can just plug that into your function. If you put this into y1, then you can either trace and find 3.5, you can use the table, or at the home screen you can do y1 of 3.5, just use function notation. And that should give you -1.625. Okay, so this is our new point, 3.5 comma -1.625. Alright, so now that's going to replace one of these 2 original points. The one that replaces is the one with the same sign as our new y value. So it's going to replace this 3 -5. Okay, because we want to keep our actual root in between our 2 bounds. So this becomes 3.5 -1.625 and we just bring down our old upper bound. Okay, so now we do the same thing. We want to do another iteration. We want to find the average of 3.5 and 4, which is 3 3/4. And then we want to evaluate our function for 3.75. So in our calculator, rounded to 3 decimal places, we get 1.234. Okay, since that y value was positive, this one's going to replace our old positive y value and its x value. So we bring down the 3.5, negative 1.625, and we replace the 4.5 with our new point. And then again, we find the average of these two, which is 3.625, and evaluate our function for that. Calculator, we get negative 0.303. Okay, and these here, these are our approximations. Okay, so our first approximation, I should say, let me correct that. These x values are our approximation. Since we're looking for the root, these x values are our, so 3.75 was our first, or excuse me, 3.5 was our first approximation. 3.75 was our second. 3.625 was our third. And then we're looking for one more. So the idea is that each time we get closer and closer to the actual root. Okay, so this one's going to replace our first order pair. So we get 3.625 and its y value. Okay, we bring down the positive y and its x that we already have. Okay, and again, we find the average of these two, 3.6875. That is our fourth iteration. And after 4 iterations, x is approximately 3.6875. Okay, if you want to find out just how close that was, if you go to your calculator and find that actual zero, then the actual zero is 3.651. So I'd say that's pretty close, within 3/100ths of a point. Okay, and we really don't need this y value here. Okay, so that's the bisection method. Here's another example on the back there. You can work this one out for practice in your notes. Let's look at our next method. Secant method is our second method for approximating roots. Same thing, we're going to start off with 2 points, one on one side of our root, one on the other. Okay, this is similar to bisection method, except instead of bisecting each of our A and B, we're going to actually find a line between them and use the x-intercept of that line as our new x-coordinate on our function to replace one of our values. So let's look at this graphically, and then we'll do the algebra associated with it. So graphically, let's say this was one of our functions. Here is the actual root. We don't know what that is, but we know it's between these two x values. So let's say we're given this and this x value. Okay, we need to know where that is on our function, so the first thing we would do is to find the y values associated with those two x's by plugging them into our equation. So we would be given the equation. And then we would want to find the equation of the line connecting those 2 points so that we could find the x-intercept of that line. Okay, that new x-intercept we would plug into our function and find its associated y value. That new y value would become, in this case, our new upper bound. So then what we would do is we would find, let's see, we would find the line between that new point and the old point on the other side of our actual root. And then once we find that new x-intercept, then we would find the y value associated with that new x-intercept and do another iteration, replace that, and then the idea is that each time our system's running kind of slow. Each time our secant line would get that much closer to the actual root. Okay, so if we did it one more time, if we found the y value associated with that x, that would be right there. So then we would do, let's see, we would connect a line from that point to that point, and then you can see it would get closer and closer to that actual x value. I apologize for the delay in the video. Okay, so algebraically, here's what we're looking at. Okay, we want to construct a line between the two coordinates that we start off with. So given an a and a b, we would need to find f of a and f of b. Find the line, find the x-intercept of that line using point slope form. And then we would take that new x, plug it into our function, find its y, replace one of our old points, and then do the same thing again. So we're finding a secant line of our function which touches our function twice. And the idea is that each secant line, the x-intercept of the secant line, gets closer and closer to our actual root. So algebraically, let's look at this. Our first example, f of x equals x cubed plus 4x squared minus 10. Okay, so let's say we're told there's a root between 1 and 2. We want to approximate it doing 3 iterations of the secant method. Okay, so step 1, let's find the y values associated with our 2 given x's. So plug those into our function. Okay, we get our points 1, -5, 2, 14. Now, find the slope between those 2 points. So if we've got our x1, y1, x2, and y2. Okay, and then do your slope formula. So we get 14 minus a -5. Okay, remember changing y's over changing x's. 2 minus 1. Then we get 19. Okay, plug that into your point slope form. That goes there. Pick a point to go in your x and your y. And then find the x-intercept. So let y equal 0. Solve for x. For our first iteration, that's going to give us 1.263. Okay, it is okay to round these to 3 decimal places in this time, since most of our approximations are going to be really serious decimals. Okay, so first approximation, So real similar to bisection method, plug that into your function, find the y value associated with it. Now that's your one of your new points. So depending on what the y value of that point is, determines which one of your originals you replace. So this is going to replace our 1, -5 point. So now we're looking between these 2 points here. So let's find the line between those 2 points, find its x-intercept. That's our second approximation. And we would do that one more time. So find its y, find the line between those 2 points, its x-intercept, and that would be our third approximation. So for this one, we would get 1.359 to the nearest thousandth for our answer. The actual root, if we found that in our calculator, is 1.36523. So that's not too shabby. That's real close to our actual root. Okay, on your note sheet, there are 3 good examples. You can practice doing the secant method. This says on a separate sheet. You can either do that in your homework notebook, in your notes notebook. We'll talk about these in class. So 2 methods for finding the approximation of roots of polynomial functions.